right, so today we're going to continue with algorithm and algorithm analysis. Just to review, remember that we went through this 5-step process, and then we went through a couple of examples. Well, we're going to continue going through a couple of examples today. I guess we covered each one of these 5 steps in a little bit of brief detail, where you identify the input and you identify the input size. Both of those are going to be automatic if you've written good pseudocode. Then you identify the elementary operation. And that one is a little bit more nuanced because you're generally looking for the most common or the most expensive or the most relevant elementary operation. And there could be more than one correct way of analyzing it. You'll just come out with a different analysis. And then 4, you determine how many times the elementary operation is executed with respect to the input size n. The 5th step here is the one that we're going to generally wait until we've covered asymptotics, but I will give a brief introduction to for each one of these examples. Please play the music. The music is done. Right? I have no idea who this is online, so never mind. Anyway. Generally what happens with algorithm analysis in a course is that you cover basic searching and sorting algorithms along with it because it keeps the problem the same and then shows you different strategies for approaching the problem and different ways of analyzing the algorithms that you develop for it. So we'll do the same. We've already done binary search. We did that in Python here last time. But we're going to go ahead and review selection sort. You may or may not have seen insertion sort before. We're going to go ahead and look at that. And then quick sort and merge sort. And then we'll come back around to binary search after we've looked at each one of these examples. Okay. Now, in the interest of time, I'm not going to develop the pseudocode from scratch. Instead, I'm going to jump right to the end and look at the pseudocode that's available in the Computer Science 1 textbook, right? Mine, right? This one is selection sort. So now let's remind ourselves of the basic idea first. And to do that, I'm going to go ahead and give myself this array example right here, okay? The way that a selection sort works is that you work through the array and you search out for the minimum element first. We're going to be sorting all these things in ascending order, or at least non-decreasing order. So the first step is you find the minimum element from 0 through 8, or more generally n-1. And so the way that you do that is you start at the beginning, right? 42 is my minimum. Then I go to the next one. 4 is less, so that's my minimum so far. 9 is not less than the minimum that I found so far, so I stay there. 4, you resolve ties arbitrarily, right? If you want to, you can go ahead and stick with the original 4 that you found, or you can go ahead and update it to this 4. I'll stick with the original 4 because 4 and 4 and 4 and 4. Do you see any difference there? No, right? So I will continue. 102 is not less than 4. Remember, this is my minimum so far. 34, 12, 2. Oh, I found a new minimum, right? I update what my minimum is. And then I find that, oh, actually, the 0 is my minimum. And at the end of that, I swap the min with the current, right? This is going to be the ith element. And in this case, that's going to be 42 and 0. At that point, I've got 0, and then 42 is down here, and I've got all the remaining stuff still here. Okay? At that point, this is sorted. Right? And then I continue with the rest of it. I find the minimum among the remaining elements, and I repeat, and I put that right here. I do it a third time, and I end up selecting the third smallest element, and I put that at the beginning, or at the ith spot. In the ith iteration of this algorithm, right, you have I minus 1 elements, right? A sub 1 through A sub I minus 1, right? And this is sorted. And then you're looking at elements A sub I plus 1, plus 1, A sub n, right? And this is unsorted. So in general, you are finding the minimum, find the min among A sub I through A sub n, right? And swap it with a sub I. In other words, a sub I and a sub min, whatever that ends up being, we're going to swap those two values. Okay? That's the idea. Here's the pseudocode that achieves that idea. Walking through and annotating it. Right? I start at a sub 1 because I'm considering on the first iteration, I am considering a sub 1 through a sub n minus, or a sub n, excuse me. Come on, there we go, a sub n. Because I need to consider all the elements to find the minimum among them. On the next iteration, I consider a sub 2 through a sub n, a sub 3 through a sub n, a sub 4 through a sub n. Why do I stop short at a sub n minus 1? Because it's already sorted. If you find the, if you've got 10 elements here, and you find the 9 smallest ones and you've already put them and arranged them, well, guess what about that 10th element? It's already where it needs to be. So I stop at a sub n minus 1. Right? Okay. How do we go about finding the minimum? Right? We'll assume that the current a sub I is minimum, and then look at the rest of the elements. This is the rest of the elements. Right? A sub I plus 1 through a sub n. And if you ever find something that's smaller, right, then you update your min index, and that's what this is doing right here. At the end of that inner for loop, at least, you swap a sub min and a sub I. There's a walkthrough of the actual algorithm. Okay. Now what we need to do is go through our 5-step process. The first two are super easy. What is the input? It's the collection A. What is the input size? And that's also encoded in the pseudocode. It's n, the number of elements in the collection. Okay. What's our elementary operation here? Now here's the first algorithm where we might have a choice, right? We are clearly doing some work in the for loop. We're clearly doing some work in this for loop. We're clearly doing some work to assign a value. None of those are going to be candidates, though. Remember that if you were to actually implement this in, say, Java or something like that, then you've got int I equals 0, I is less than n, I plus plus, right? So what are you actually doing here? You're doing an assignment. You're doing a comparison. You're doing an addition and then an assignment, right? But all of that is necessary for the control structure of the algorithm. Within that loop, you are doing work. Within that loop, you are doing work. So look for the most common or most expensive thing. One candidate would be the comparison on line 4. Another reasonable candidate would be a swap on line 8. Now, if you put on your engineering cap and think, you know what, memory I/O is way more expensive than a comparison and jump assembly code operation, right? Well, then maybe, yeah, swaps. That's where the most expensive thing, and maybe I want to optimize for that. Right? And there are plenty of examples where that is true in real life, and that would be a perfectly reasonable answer too. You would just come out with an analysis that is for memory I/O for swaps. Right? What I'm going to do is I'm going to go ahead and keep it simple, and I'm going to go ahead and go with the elementary operation being the comparison on line 4. Because I want to be this to be comparable to linear search, binary search, and all my other sorting algorithms. Okay? So this is going to end up being the comparison on line 4. Good pseudocode are numbered so that you can make reference to those line numbers. Okay? Just like regular code. All right. Step 4. How many times is that executed with respect to the input size? So for that, let me go ahead and give myself some more real estate here. All right. So if I'm looking at line 4, how many comparisons just on line 4, or the block on line 4, how many comparisons am I doing right there? If I ignore everything else that's surrounding it? 1. You're doing 1 comparison on line 4. Now the question becomes, this block right here, how many times is that block executed with respect to the outer for loop that it's that it's inside of? There we go. Okay, so you're immediately jumping to the end answer. Let's go ahead and keep it general. And you've got j running from I plus 1, I plus 2, I plus 3, I plus 4. Ultimately, that's going to be a summation for j running from I plus 1 up to n. Now, you immediately jumped to the answer because you said, well, this is just 1 plus 1 plus 1 plus 1. How many times? N minus I times. Let's walk through that a little bit, though. Right? I plus 1 to n, one time each, and so the total is going to be n minus I or something like that. We'll expand that out here in a moment. Right? So all of this is going to be line 3. Right? Okay. Now expand that out further and look at the entire outer for loop. Right? Right. Adjust that as you will. Right? And that's going to be a summation. Right? I'm basically putting a parentheses around here, but parentheses aren't necessary with summations. And you're running this from I being 1 up to n minus 1. Okay? Now it's a simple matter, and this entire thing now is starting at line 1. That's the total number of comparisons. Right? With respect to n, the input size. All we need to do is solve that summation, and we've got our answer. Right? Okay. Copy. And let's solve the summation. Come on. Paste. There we go. In fact, I will go ahead and get rid of this line right here, and I will get rid of my parentheses here, because summations of summations are the parentheses are implicit. Let's focus first on this inner summation right here. Right? Let's solve that down here by itself. Okay? Now, what is this equal to? This is 1 plus 1 plus 1 plus 1 plus ... plus 1. How many times? So this one will match up when j is I plus 1. This one will match up when I is I plus 2, I plus 3, I plus 4, ... when it's n. Right? So how many 1s are there total there? Well, think of it like, it's not that easy to see right away, maybe. But if I were to start at 1 instead of starting at I plus 1, it would be really easy, right? If I started 1, 2, 3, 4, 5, ... to n, and I said, well, this is 1 plus 1 plus 1 plus 1 plus 1 plus ... plus 1. How many 1s are there now? N, right? Because you started at 1. I didn't start at 1. I started at I plus 1. So what did I leave off? I, right? If I went one more here, I plus 1, right? Then I want to get a hold of how many there are here in this region, right? This region right here, because that's what my summation actually is. Well, how many are in this region that I skipped? I. So if in total I have n of them, and I skip I of them, then guess what? This is n minus I. Okay. Great. Zip, zip. There we go. So this is equal to, don't lose your outer summation here. I is 1 up to n minus 1 of n minus I. Now I will put that in parentheses. But the summation of sums, and this is a summation, right? N and plus negative I. You can split that up into two summations. And so that will be the summation of I from 1 up to n minus 1 of n minus summation of I 1 up to n minus 1 of I. Okay. Tell me about that first summation. Same trick that we just did before. N plus n plus n plus n. How many times? we go from 1 up to n minus 1. So n plus n plus, if it was 5 times, it'd be n plus n plus n plus n plus n, 5n. If it was 10 times, it would be 10n. It's neither of those things. It's n minus 1 times, so it's n minus 1n. Okay? Now what about that second one? 1 plus 2 plus 3 plus 4 plus 5 dot 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 to n minus 1. Do we remember a tool that we covered last time? I thought we covered it before the iPad died. Gauss's formula? Yep. I equals 1 up to n of I, the summation of natural numbers. This is the quintessential example of an inductive proof, right? You can prove this by induction. It's usually the example that gets thrown out for the first inductive proof that you see. Let's say in 235. You've done induction? Yes? Okay. All right. And it is simply just n times n plus 1 all over 2. We do not go all the way up to n. We only go up to n minus 1. So n minus 1, n minus 1, and we have what? N minus 1 times n minus 1 plus 1 cancels. So there we go. The second one is half the first. So we have in the end n minus 1 times n all over 2. If you want to expand that out, it'll be 1/2 n squared minus 1/2 n. At the end of the day, what's the most important term here? N squared. And so step 5, preview, this is a quadratic algorithm. Right? That's an analysis, step 1, 2, 3, and 4 for selection sort. Okay? Let's look at another algorithm. Insertion sort. There's the code. We'll come back and annotate it here in a second. Let's think about what, how it works. Okay? So here's my original array. I'm going to put this up here. There we go. All right. So here's the general case, right? So on iteration I, A1, A2 dot 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 A sub I minus 1 is sorted. This will be our inductive assumption, right? Why do we like to do induction in 235, or why do we like inductive proofs? Because induction is nothing more than a loop, right? You have to think about the general case of your loop. That's the ith iteration. Now you have to prove I implies I plus 1, the next iteration, right? So if you have an assumption on your loop, we call them loop invariants when applied to algorithms, then you need to show that that assumption holds on the next iteration too, right? So this is my assumption that I've got A1 through A minus 1 sorted. The way that that looks is, again, A1 through AI minus 1. And we're going to be looking at the ith element. And what we need to do is we need to insert A sub I into, among A1 through AI minus 1, right? That's why we call it insertion sort. How do we go about doing that? Well, let's look at an example here. We'll look at this example right here through a couple of iterations. Okay. On the first iteration, by the way, when I'm only looking at one element, by definition, it's sorted. I don't need to do anything. 42. If you only had an array with one element, there's nothing to do. It's already sorted. So now let's look at the actual first iteration of this algorithm, where we're looking at 4. And we're only looking at this, these two elements. Is 4 where it needs to be? No. Nope. We know that by comparing it to the first, to the next previous one, and shifting it down. When we have 4 and 42, guess what? We're done. We go on to the next element here. And that's where I'll start simulating this algorithm. 4, 9, and what was the next one? No, 4, 42, 9. All right. 4, 42, and 9. Again, this is the sorted area. And we're considering this element here and we need to insert it where it needs to be. I will make one comparison to see, oh, 42 and 9 are out of order, so I swap them. Right? Or more generally, what we're actually doing in the pseudocode is I'm going to shift 42 up to make room for 9. Then I compare 9 to 4 to see, oh, that's where I end up inserting it. Right? So 2 comparisons here to see that the new configuration should be 4, 9, and 42. That's the second iteration of the algorithm. Okay? What's the next element? 4. Okay? How many comparisons am I going to make to shift this down? 1, 2, 3, and then I can break ties by shifting it or just be done. 4 and 4, 4 and 4, who cares? Right? And so 3 comparisons here. Right, let me highlight this in red. 3, 2, right? It's not always going to be the same. When I've got this, I've got 4, 4, 9, and 42. There we go. Done, done, done. What's the next element? 102. How many comparisons do I need to make to shift this down? 1, and then I don't shift it, right? So 1 comparison in this case. Okay? So I'm left with 4, 4, 9, 42, and 102. There we go. Next one is 34. 1 comparison, 2 comparisons, 3 comparisons to see that I should insert it right here. Right? So it's adaptive. Sometimes I get away with only 1 comparison. Sometimes, for example, if my next one, what is the next one? 12? Well, let's suppose that the next one is going to end up being 0. How many comparisons am I going to have to make? All the way back down to the end here. Right? Sounds very much like linear search. Right? Sometimes you get lucky and you only have to make 1 comparison. Sometimes you get unlucky and you have to make a lot of comparisons. Let's take a look at the pseudocode in closer detail here now. Okay? All right, let's annotate it. Why am I starting at 2 here? Yep, because a sub I by itself is already sorted. I do go up to n in this case. Why? Because the last element, if I've sorted the first, n minus 1 of them, I still need to make sure that this is inserted in the proper location. Okay? What I'm doing here is creating a temporary variable because I don't actually want to swap them, right? What I'm going to do is I'm going to shift things over. So I take the ith element, right, and I put it into this temporary variable that I call x, so that I'm always comparing x and I don't have to, talk about a sub I anymore, right? It's much easier that way. I then start a j index variable here at I. Why? What is j going to do? Well, again, if you've got a1 through I minus 1 here, you are going to start at, here's a sub I, right, that you've already saved off into x. You are going to start at, do we need to start at j? Or I? I guess not. We could start at I minus 1, but we'll go with this pseudocode here. Basically, j is going to run and go down. That's why we're decrementing it each iteration here. And we are shifting things up. What we're doing is we're taking a sub j and putting it into a sub j minus 1, and we're putting it into a sub j. We're shifting things to the right as we go as j goes down here. Right? When do we stop? When either you've fallen off the edge, that's the first condition right here, or the x that you've got here, that's where it belongs. And if that's where it belongs, that's where you put it, on line 8. Okay? That's the annotation. That's the walkthrough of the pseudocode. Now, analysis. Same 2 steps. What's the input? It is A. What's the input size? N. What is the elementary operation here? Let's go ahead and stick with comparisons. Is it this comparison right here? No, that's necessary for the control structure of the algorithm. That's just a bounds check. Are you about to fall off the face of your array? Okay. This is the real comparison right here on line 4. Right. How many times is that executed with respect to the input size? So let's go ahead and focus first on this while loop. How many times does this while loop execute? Here's where the art comes in, right? It's kind of like linear search. Sometimes you get lucky. What's the minimum number of comparisons? 1. Right? Do we always want to assume the best case scenario? No. Let's go ahead and think about the maximum, and in other words, worst case scenario comparisons. Right. Now again, let's visualize this. Here's a sub I, right? And I'm comparing it to a sub 1 through a sub I minus 1. Right? I need to find out where it gets inserted. Right? Maybe it's inserted here, maybe it's inserted there, maybe it's inserted there. The worst case scenario is where I have to shift it down all the way to the end. In which case, how many comparisons did I end up making? I minus 1. Why I minus 1? Because there are I minus 1 things in the array that have been sorted so far. So this is I minus 1. Okay. How many times is that while loop executed with respect to the outer for loop here? Well, it's executed I running from 2 up to n. That sets us up for, remember that it was I minus 1. This is the inner while loop. That sets us up for a summation here for I running from 2. Remember, we skipped 1 because who cares? An array of size 1 is going to be sorted automatically. But in this case, we went up all the way to n. And so this was the for loop. Right. Same tricks as we did before. Split up your summation. I running from 2 up to n of I minus I running from 2 up to n of 1. The second one should be really easy. 1 plus 1 plus 1 plus 1. How many times? N minus, it's careful, we start at 1, but we do include 2. So 2, 3, 4, 5, 6, 7, 8, 9, up to n. So n minus 1. Don't lose your parentheses. I think I might have lost my parentheses in the morning class and gotten it wrong a little bit. Right. In case I didn't go all the way through with all the algebra. So it didn't matter. Right. What about the second one here? That looks like Gauss's formula to me again, except that I've skipped 1. So it's 2 plus 3 plus 4 plus 5 plus plus n. So Gauss's formula tells me that that's n times n plus 1 all over 2. But if you skipped 1, just subtract 1. Right? Do we want to do the algebra? There's some a, n squared, plus b, n, plus c. I don't know what a, b, and c are. Do the algebra yourself, or throw it into Wolfram Alpha and verify. Do the algebra yourself, then throw it into Wolfram Alpha to verify your algebra. Right? That's the best answer. What's the most important thing here? Again, n squared. So from one perspective, you could say, well, you know, it's not. In the worst case scenario, it's no worse than selection sort. In practice, however, it is far better to use insertion. If you have to choose between selection sort and insertion sort, you choose insertion sort, because in practice, there's going to be another 1/2 out front here when you look at the average case. Remember, you shouldn't always look at the best case scenario, but you don't always have to look at the worst case scenario. You can look at the average case scenario. And when you look at that, instead of I minus 1, it's going to be I minus 1 divided by 2 on average. Okay? And it's a little bit more involved than that. But ultimately, at the end of the day, the coefficient sitting out front here for insertion sort is going to be half as big in practice as selection sort. So when you go to test your implementations in your lab tomorrow, you'll witness this as an artifact of the actual tests that you run. Insertion sort is going to beat selection sort. Quick sort is going to beat both of them, right? And you're going to have this hierarchy in practice matching the theoretical analysis that we're doing here in class, right? That's insertion sort in worst case. Best case scenario, on average case scenario though, it's still going to be order n squared, but again, this thing out here is going to be smaller. A is going to be smaller. Okay. All right. Before we look at the pseudocode for the next one, let's remind ourselves how quick sort actually works. Quick sort. All right. Here's the idea. You choose a pivot element. And for me, I'm just going to select the first one. All right, there's my pivot. And what you do is you partition things that are less than P, I'll call it the pivot element P, go to the left. Things that are greater than P, go to the right. And then you place P right in the center of it. So in this case, 42. What I'm going to do is I'm going to go through the rest of the array, and I'm going to put things that are smaller than it to the left, things that are larger than it to the right. And what will I have after at least the first iteration of this? 4, 9, 4. 102 goes over here. 34 is less, goes over here. 12, 2. And then I place the pivot element right in the middle. Oh, sorry, I missed 0. There we go. So stretch you over here. There we go. To 42. 42 is where it needs to be. Don't move it anymore. All right. What you do now is you recurse. So recursion, right? At least the way that we're going to present it, use recursion. This is the left partition, and this is now the right partition. Tell me about that right partition. Is there any more work to do? Nope, because it's an array of size 1. If you have an array of size 0, same story. It's, by definition, it's sorted. But here on the right side, we have some more work to do. Oops. Come on. I think I copied it correctly. Let's find out. Paste? Nope. Darn it. I only want you. Copy. Paste. Ah, good. It's way more judicious than it was being before. I'll even increase the size there. Okay? All right, same story here. This is just in the recursive phase, right? I've recursed on this smaller array, divide and conquer strategy. There's my new pivot element, P. I go through the rest of it and I partition it. Things that are larger, 9, go to the right. Things that are less or equal to, go to the left. 4, 34, 12, 2, and 0. And then I put 4 where it needs to be. Recurse on this left partition, recurse on this right partition. Dot, 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 until you get down to an array of size 0 or 1, in which case you can stop. Or you could even go with a hybrid approach. If you get down to an array of, say, size x, where x is a tunable parameter, switch over to insertion sort. Because at some point, the recursion stops to pay off, starts to become more expensive than the actual payoff that this divide and conquer strategy gives you, right? So you can have a hybrid approach where you do the divide and conquer, but you get down to an array of size, say, 20. And then instead of recursing anymore, you just switch over to insertion sort or something. Right? Okay. Let's take a look at the pseudocode. It's actually a little bit different than what you've seen before, maybe. Quick sort. There we go. Simple. Right? What is each one of these things doing? Well, this partitions, right? And tells you what the index of the pivot element here. Right? And then you can recurse on the left and the right. How do you keep track of that? Just through indices. L and P minus 1, P plus 1 up to R. You're given L and R as part of the input. So why don't we include P in this? Because that's where it belongs. Right? That's the pivot element. Okay. When do we stop? I've got L and R, right? I'll recurse, 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 recurse. They're starting to close in on each other. When they are equal, what does that tell you about the size of that subarray? It's of size 1, right? When this is strictly less than this one over here, left is strictly less than right, then we have at least 2. We could have 3, 4, larger, right? But they have not met in the middle yet. What happens if they go past each other? Yep, it's an empty array and we're done anyway. That's why we're only checking for strictly greater than here. Okay? All the magic is done here in the partition. Let's take a look at what that looks like. By the way, all the pseudocode is from the Computer Science 1 textbook, so you can go back to that in your lab. You can either use that as a basis for your algorithms. I think I might even have C code in there that you can adapt. But otherwise, you can also look at Wikipedia or something like that to get their version of these things. This is a little bit different than what I described graphically. It's called an in-place partition. Okay. So what this is doing, let's go ahead and go through this and annotate it. Right? So first of all, we'll choose the leftmost element as the pivot. Okay. And then we set up our I and J. We start J, if this is my subarray right here, we start J at the left, and we start I over here. This is A sub P. That's my pivot element. So I'm going to ignore the pivot element. And I'm going to start I and J at both of these ends here. Okay? Now, while I is less than J, in other words, while I is still over here and J is over here, when they meet in the middle, then I'm done. I'm done partitioning. It could be that, these things belong over here. These things belong over here. But when I get to 2 things that are on the wrong side of each other, I'm going to swap those. That's what these inner loops do. Right? This one, that's an interesting spelling of it. While A sub I is on the correct side, move I over. Right? I will be moved over, I will be moved over, I will be moved over, until you find something that's on the wrong side. Okay? While A sub J is on the correct side. Correct? That is the right side. Then move J over, etc., etc., etc. Okay? When you found an A sub I, say that our pivot element here is, say, 50, and you found an A sub I that is 75, it's on the wrong side. And you found an A sub J that is 25, it's on the wrong side. I didn't need to move these things over here. I didn't need to move these things over here. I just need to move these 2. And so I end up swapping A sub I and A sub J. Continue until I and J might, okay, I found one guy that's on the wrong side. I found another guy that's on the wrong side, swap. Continue. Finding pairs that are on the wrong side and simply just swapping. Right? Don't swap if you don't have to. If it's already on the correct side, right, you don't need to move it. Right? Once I and J have met or passed, you are done with the partitioning. You may then need to swap the pivot element out. And depending on where your I and J ended up, right, are you going to put the pivot element here, or are you going to put it the one adjacent, right? And that's just a small little technical detail here that I'll leave for you to examine yourself. Right? Again, if you want to look at an actual example, let's go with this. Right? And I don't like this, so let's go ahead and white this out and give myself a different number. What would be nice? 10? There we go. Okay. So now 10 is my pivot element. I start my I over here. And in fact, give myself some more room over here. The pivot element is 10. I start my I right here, and I start my J right here. Okay? Now I'm going to go ahead and examine the left part here. Okay? Oops. Why did I lose that? What? Oh, I know why. Because I'm trying to highlight too much. All right. Erase you and put you off the image right there. There we go. Now I'll be able to move it. Okay? So is 4 on the correct side? Remember, it's less than 10, so it needs to be on the left side. So I move over. Is 9 on the correct side? It's less than 10, so yes. 4 is on the correct side. 101, though, that belongs on the right side. So I stop incrementing my I. That's the first, oops, come on. That's the first while loop right here. Okay? Then, I'm going to have to erase you too. I have my J over here. There we go. 0, is that on the correct side or not? Nope. So I'm done, and what do? Swap. And now I have 102 and 0, so 0 and 102. There we go. Now your I's and J's continue, right? 34 is on the wrong side with respect to the left side. 2 is on the wrong side, so I end up swapping those. And then I meet in the middle. You get the idea. Okay? Now, let me get a clean quick sort here. There's the main routine. Here is the subroutine over here. Right? So we've got a little bit more complex analysis on this. We're still going to do it with respect to the number of comparisons. Thank you. But we have a subroutine and we have recursion. How do we go about setting quantifying the number of comparisons made by this algorithm in total? Okay. I'm going to start by defining a recurrence relation. Let C sub n be the number of comparisons, comps, by quicksort, QS, on an array or collection of size n. Okay? Let's look at the main routine here first of all. What about partition? Are we making comparisons in the partition? Yep. Is this thing on the right side, the correct side? I don't want to say right because of the right versus left. Is this thing on the correct side? Is this thing on the correct side? Right? Yes, 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 no, oh, no, no. Okay, swap. Right? And keep going. So there is a number of comparisons being made in this subroutine. And then we have to go over here and examine that subroutine. But also, I'm making a recursive call to quicksort twice. Right? Okay. So how do I get a handle on this? Well, let's go ahead and do the easy thing first. How many comparisons do we make in this subroutine? Let's go ahead and think about this. Not code line by line by line, right? Because I've got while loops within while loops, and I've got separate while loops, etc. Let's just think about it in general in one iteration here. If there are, say, n elements here, oops, there we go. How many comparisons do I need to make to partition it? Remember, I just not randomly, but I deterministically, arbitrarily, I should say, choose the first pivot element. And then I go through all the other elements here, I and j. And I'm making comparisons to the pivot element. Right? I'm moving this over, moving this over, moving this over, moving this over, until I get down to I and j, both agreeing and both referring to the same element here. So how many comparisons did I make? n minus 1. Total number of comparisons in partition will be n minus 1. The size of the array that you're partitioning. Okay? So let's go back over here. N minus 1. And this is the number of comps in partition. Now, we still have two other things here. Remember, this comparison right here is for the control structure of the algorithm, right? L is less than R. Don't worry about it. Okay? I've taken care of line 2. Now what about lines 3 and 4? Lines 3 and 4 being the quicksort and the quicksort, the two recursive calls. Right? Let's make some assumptions. So, best case, best/average case, average case. Your partitioning, it partitions into two roughly equal sizes, equal arrays, subarrays, I should say, right? Well, if you have two roughly equal subarrays, and the original array was n elements, about how many are in each now? N divided by 2. Okay? Do we know how many comparisons quicksort takes on an array of size n divided by 2? Yes, that's how we define C. So C of n divided by 2 plus C sub n divided by 2. Right? This is the recursive cost of the left partition, and this is the recursive cost of the right partition. All right? Now, new, let me go ahead and collapse all that. Again, C sub n is the number of comparisons for quicksort in the best case or the average case. There are two recursive calls on arrays of size n divided by 2. And then there's a non-recursive cost of n minus 1 comparisons. Okay? In 235, have you talked about how to solve recurrence relations yet? No? Eventually you will. Difference functions. Have you taken differential equations? Not yet. Many of you haven't yet. You'll talk about how to do them on a continuous domain. It's the same exact stuff, except that in differential equations, because it's on a continuous domain, sine and cosine come in because of Euler's identity, right? And I comes into the play too, imaginary numbers. Don't worry about it. I don't want to solve it either, right? Instead, we bring in this tool called, and where are you? Do I have it here? All right. Where are you? There we go. Master theorem. It's a misnomer. It's not a master of anything. In fact, its use is quite limited. It says that if you have a recurrence relation of this form, then you can apply this theorem to get an asymptotic analysis of it. Again, we haven't talked about step 5 yet, so we'll keep that on the back burner for next time. But basically, it's just plug and chug. A is 2. B is 2. F of n is bounded by a linear function, so this other d ends up being 1. You can plug and chug and find that this case applies and be done. Don't worry about it. What about the worst case scenario? The worst case scenario, I'll just tell you, is when you end up partitions into unequal partitions. So one partition will be of size 0 and the other one will be of size n minus 1. Right? You can imagine what that would look like. 2, 5, 7, 13, 29, 70. If it were already sorted, and there's my partition, where does everything go? To the right. What about in the left? 0. Partition again, around 5. Everything goes to the right? and there's nothing to partition in the left. Right? Partition again, everything goes to the right, everything goes to the right, everything goes to the right. That is one of the worst case scenarios. We set up our recurrence again. C sub n is equal to, now to partition, it's still going to cost me n minus 1 comparisons. Now there's only one recursive call technically, because if I make a recursive call on an array of size 0, it doesn't do anything. So that's 0. I can immediately say, nope, who cares? What about the other side? How many elements are still remaining in the other partition? N minus 1. Right? Now you can solve this using 235 material. But again, you said no. This is a linear, non-homogeneous recurrence relation of degree 1. Right? And it comes out to ... Guess what? Our old friend Gauss. N plus times. It ends up being n times n plus 1. It might be minus 1, I'm not sure. Divided by 2. Which is going to end up being order n squared. Don't worry about the details. Right? You can assume you can assume the average case for quicksort. Right? In which case it's going to end up being n log n from our second phase here, which we'll cover next time. Okay? All right. Any questions so far? No? Let's go back to binary search then, right? So binary search. Here's the code that we made from last time. Right? That's another nice while loop. But it's adaptive, right? When do I get down to 0? Did we do the analysis? I forget. No? Okay. Let's do the analysis on this one. Right? Let's do it visually. All right. So what I'm doing again is I'm going to the middle element, right? A sub m. And everything over here is less than a sub m. Everything over here is greater than a sub m. Right? So let's start by iteration, thinking about each iteration. There's a first iteration, there's a second iteration, there's a third iteration, et cetera, et cetera, et cetera. Then let's think about the size of the array. And I am comfortable calling this an array instead of a collection. Why? Binary search only works on arrays. It only works if you have random access. Think about running binary search on a linked list. Can you jump to the middle element easily? Nope. You have to start at the beginning and then traverse half of the list, and you're already linear to do that. Right? So don't bother running binary search on anything other than an array-based list. Right? Initially, how big is the array? N elements. Okay. On the second iteration, what have we done? We've effectively eliminated half of the elements, right? So we repeat and recurse, or we repeat on only one half of the array. How big is half of the array now? N divided by 2. And let's keep track of the number of comparisons that we've been making. We made one to cut it in half. On the next iteration, we make one comparison, right? Let's go back over here. Where are the comparisons do you see in this Python-y pseudocode? I think it's actually correct, isn't it? Correct Python? Oh, no, it's not, because equals is an assignment operator. I must not have copy-pasted the correct one, right? Yeah, okay. So I was writing the pseudocode, and then I said, screw it, let's go ahead and take it over to Python. And then I made changes to it, and I never copied it back. So this is pseudocode. This is not Python here, right? I'm making a comparison here, but I'm also making a comparison here. Is that really two comparisons? Yeah, well, it could be that one that this happens and it's not equal, and then this one happens, but certainly there's not going to be a third comparison. So even if you started out with 3 comparisons, you can cut it down with 2 comparisons by just making it an else instead of an else if. Really, it's one comparison though, right? Think about how you do this in practice. You write a comparator function, or you write a comparator class, or you have one function call that compares two things and returns something negative, positive, or 0, depending on the relative ordering of these two things in your hand. Right? Determining whether or not it's negative, positive, or 0 is necessary to the control structure of the algorithm. So keep it simple. No, it's one comparison. Right? So on the first iteration, there's one comparison to cut it in half. On the second iteration, there's one comparison to cut it into, how big is it now? N divided by 4. Fourth iteration, one comparison to cut it down to n divided by 8, dot, dot, dot. On the kth iteration, how much have I cut it in half by? 2 to the k, making one comparison there. Right? When do I stop? What's the last iteration? When the size of the array becomes 1, right? And I make one last comparison to see, is that the guy that I'm looking for? Right? So for what k does this become 1? So, okay, let's do the math properly. You jump into the answer here, right? How many? This is the number of iterations. The number of iterations will actually tell me how many comparisons. Why? I do one comparison for each iteration. So if I know the number of iterations, I know the number of comparisons. Solve for k. Help me. Right? How do I get rid of that 2? Log base 2, but we're self-respecting computer scientists, so we don't write 2. We just say n. All of our logs are base 2 implicitly, and that's equal to k. So in other words, the number of comparisons is equal to log n in the worst case. Of course, you could get lucky and you're finding the median element already, right? Jump ahead to step 5, log n. That's the iterative version. Let's think about the recursive version. Binary search recursive, there we go. Here's the same algorithm, but instead of using a while loop, it uses recursion. Exact same logic here though, right? If L has surpassed R, right? They've gone past each other. We output, nope, we didn't find it. Otherwise, L is over here and R is over here. So what we need to do is we need to compute the minimum, or the, sorry, not the minimum, but the middle index. And I'm using floor here, L plus R divided by 2, right? This is pseudocode, so it's okay to do this. Never do that in practice because it's susceptible to overflow, et cetera, et cetera, et cetera, right? And then I'm making the same checks here. If that's the thing that I'm looking for, I got lucky and I'm done and I output it. If the thing that I'm looking for is greater than the middle element, then I recurse on the right side, right? This is the right half. Otherwise, I go to the left half. And you can see that I'm modifying the left index, leaving the right index alone, or leaving the left index alone and modifying the right index. I'm zeroing in on it. Yeah?
So is binary search usually written?
If I were writing it, I would write it how I started out with a while loop, right? I'm showing this so that we can get more practice setting up a recursion, and we'll come out to the exact same answer, right? So, give myself some more real estate. Oops. There we go. Not too big, small. There we go. All right, same idea. Let's go ahead and set up a recursion here. Let C sub n be the number of comparisons by binary search on an array of size n. Okay? So on one iteration, we already said that, well, there's this comparison and this comparison, but let's just roll that into one. That's one comparison, right? And that's lines 5 and 7 combined. Plus, Now, we make a recursion, don't we? We make a recursion here, and we make a recursion here? Is that an and? No, we make one or the other, right? So we make one recursion. How big is the resulting array in that recursion? Half the size, right? This, once again, is a non-linear, non-homogeneous recurrence relation. You can pull out your 235 material and try to solve this. When you ultimately end up solving it, guess what you get? Log base 2 of n, right? Because we already did the analysis on the other version of it. But otherwise, you pull out your trusty friend here. Oh, where is it? There we go. Master theorem. There we go. And you realize that it's of this form. Right? You make one recursive call, so A is 1, on an array of half the size, B is 2, and you do an amount of non-recursive work that is proportional to n to the 0. So D ends up being 0, and you have the exact same answer as before, but this term disappears, and guess what you're left with? Log n. Right? Again, that's a preview. We'll actually go into formal asymptotics here with an actual definition on Thursday. Okay? Any questions? No? All right. Then have fun with sorting algorithm implementations tomorrow in your lab. Again, either use the Computer Science 1 textbook as a basis or go out and find some implementations. But the more important thing is that you'll be doing the experiments to see what's a good sorting algorithm, what's a bad sorting algorithm, and I think that you'll be pleasantly surprised.